Okay, this is my demo 7. I'll be demoing on 8A and 8B. For 8A, the competency is I can draw timing diagrams for 3 types of flip-flops, a JK, a D, and a T flip-flop with asynchronous controls. So for my JK flip-flop, here is my timing diagram, and pretty much I'm just going to go line for line and explain what each one of these is doing. So for the preset, it's an asynchronous input. When pre is low, meaning active, it immediately sets Q equal to 1, regardless of the clock, J or K. And so in this diagram, the pre starts low, then goes high, and later drops low, and then high again. So each time that pre goes low, meaning active, Q is immediately set to high. And you'll see that down here. For the clear row, CLR, this is another asynchronous input. When clear is low, meaning active, it immediately resets Q equal to 0, overriding all other inputs. In the diagram, clear is active low during a few brief intervals. Each time clear goes low, Q drops to 0 instantly, regardless of the clock or JK values. For J, the input, because it's a JK flip-flop, our first J input, it's part of a synchronous JK control evaluated only on the rising edge of the clock. So when J equals 1 and K equals 0, it's on rising clock edge and Q is set. When J equals 1 and K equals 1, on rising clock edge, Q toggles. And when J equals 0 and K equals 0, there's no change. So this diagram shows J toggling high and low, so toggling high, low, high, low. And this impacts Q only when the clock rises. So when you see clock rises, it impacts Q. For my K input, same timing rule as J. It's evaluated only on clock rising edge. So when J equals 0 and K equals 1, Q is cleared, meaning set to 0. When J equals 1 and K equals 1, Q toggles. And the diagram shows when K is high-low, affecting Q accordingly during clock rising edges. So same timing rule as J. So for my clock line, rising edges are the only time Q reacts to J and K. So when the clock rises, the flip-flop checks J and K and updates Q unless pre or clear are active. If pre or clear are low during the clock edge, they override the JK logic. So that's how the clock line works. For my Q output, which is my flip-flop output, when pre is 0, Q is set to 1 immediately. When clear is 0, Q is reset to 0 immediately. Otherwise, changes on the clock rising edge based on J and K. So when J is 0, K is 0 is no change. J is 0, K is 1, Q is 0. J is 1, K is 0, Q is 1. J is 1, K is 1, Q toggles. So that is my timing diagram for a JK flip-flop with asynchronous controls. And now here's my D flip-flop. So we have our D input, our clock line, and then our Q output. And so I'll do the same thing. I'll just go each line and explain what it's doing. So D, this is the input value that gets sampled on the rising edge of the clock. Whatever value D has at the rising edge of clock becomes the new Q. So if D equals 1, Q becomes 1. If D equals 0, Q becomes 0. For my clock line, right here, controls when data is sampled. Only rising edges, low to high transitions of the clock matter. At each rising edge, the D flip-flop copies D to Q. So copies D to Q, and you can see that here. Copies D to Q. For my Q output, follows D at the rising edge of the clock. Between clock edges, Q holds its last value. So between clock edges, Q holds its last value. You'll notice the Q changes only when clock rises, and it takes on the value of D at that moment. So whenever the clock rises, takes on the value of D at that moment. So it rises right here, value of D is low, value of Q is low. Right here, rises, value of D is low, value of Q is low. So that is my D flip-flop, and then my T flip-flop timing my T flip-flop timing diagram. I'll do the same thing, just go line for line. For T, this is the toggle input. This input determines whether the flip-flop toggles its output. So if T equals 0, there's no change in Q on clock edge. When T equals 1, Q toggles on each rising edge of the clock. So it'll toggle on each rising edge of the clock, as you can see here. For the clock line, as with the D flip-flop, changes happen only on the rising edges. So any rising edge is when changes happen, and the T input is only evaluated during those edges. And then for Q, T equals 1 at clock rising edge, Q toggles, 1 becomes 0 or 0 becomes 1. And then when T equals 0 at clock rising edge, Q holds its value. So you'll see Q only changes when T equals 1 and clock rises. So pretty much T equals 1, Q will toggle from 1 to 0 or 0 to 1, and then when it's 0, Q will just hold its value. So 0, Q holds its value, 0, Q holds its value. When it toggles, that's when it changes from 1 to 0 or 0 to 1. So that is 8A timing diagrams for 3 different types of flip-flops. For 8B, the competency is I can analyze a given sequential circuit to determine its operation. And so I have a circuit built in Logisim, and we'll go to that, and we will analyze it. So some components involved. Just looking at the circuit, we're just going to look at it and analyze it. We see that we have a J and a K input, a J and a K flip-flop, a clock, a clear button, and an output of Q. So the behavior of the flip-flop is determined by the values of J and K, and it toggles its output on the rising or falling edge of the clock signal. So the operation of a JK flip-flop can be summarized as when J is 0 and K is 0, there is no change. So as we can see here, there's no change. When J is 0 and K is 1, it's in reset. So Q is still going to equal 0. So we'll change K to 1. Q is still going to equal 0. And then when J is 1 and K is 0, Q should equal 1. We'll see that here. Yep. So now Q is equal to 1. And then, so that's in the set mode. And then when J is 1 and K is 1, it's in toggle mode. And so the Q changes state each clock impulse. So we'll change that to 1. And we see we change to 0 to 1. And then we can also see that there's clear button, and so if we press that, or sorry, I'll come back to that. So we'll change that back to 1. So based off of that we can analyze it and determine that this is a 1-bit binary counter because it counts between two states, 0 and 1. It achieves this by toggling between these states on each clock pulse. This means the flip-flops will flip from 0 to 1 and from 1 back to 0, creating a binary count. For a 1-bit binary counter, the JK flip-flop is configured to toggle on every clock pulse. This is done by setting both J and K equal to 1. Okay, so that explains that. Sorry, I'm looking at my notes. So now that we know the operation of this circuit and what it does, now we want to understand why the circuit acts this way. And so the behavior of a 1-bit binary counter using a JK flip-flop and a clear operation is a result of how the JK flip-flop works and how its input interact with each other and the clock signal. So we got to understand the JK flip-flop first. The JK flip-flop is a type of flip-flop which has two stable states, a set and a reset. So when Q equals 1, it's in set, and when Q equals 0, it's in reset. The flip-flop has two primary inputs, J and K, as well as a clock input, a clear input, and a preset input. The behavior of the flip-flop is defined by the why does the JK flip-flop toggle? The core idea behind that is when both J is 1 and K is 1, the flip-flop toggles at each state. Because on the rising edge of the clock, the flip-flop changes its output Q from 0 to 1 or from 1 to 0, depending on the current state. So if the current state is Q equals 0, the output chain will change to Q equals 1. If the current state is Q equals 1, the output will change to Q equals 0. And then, so I said we'd get back to this clear. So why does the clear input affect the circuit? The clear / otherwise known as reset input is an additional control signal that can force the output Q to equal 0 regardless of the state of the clock or J and K inputs. This is a crucial feature because it allows you to manually reset the counter. So when the clear input is active, typically 0, it overrides the normal operation of the JK flip-flop and forces the output Q equals 0. When the clear input is inactive, typically 1, the flip-flop behaves normally according to the state of the clock and the JK inputs. And we already went over how this 1-bit binary counter works, and so yeah, that is my analysis on this sequential circuit and why it behaves the way it does.